Welcome to the third in our series of quantum reality conversations. In case you missed the first two, feel free to check them out, but also feel free to stay here as I'll now give you a brief summary of where we have gotten so far. All right. In our first conversation with philosopher Elise Kroll, we discussed the basics of quantum mechanics, namely that the theory has at its core the idea that the best you can ever do in our reality is make probabilistic predictions. Before an appropriate observation or measurement or interaction, the world is described by a quantum wave function that contains within it an unfamiliar mixture embracing many possible outcomes, like particle here and here. You go left and you go right. And only through observation or measurement or interaction is the reality we have access to coaxed into a single definite outcome. But how that transition from a world chock full of many possibilities to one in which only one outcome is observed and experienced, how that transition actually happens, that remains mysterious and is called the quantum measurement problem. Okay, we also explored how through quantum entanglement, reality has what we call a non-local quality. That is, what you do here can have an instantaneous quantum impact on something way over there. And such non-locality, we found, can thread not just through space, but also through time. All right, in our second conversation with physicist and author Sean Carroll, we explored a number of proposed resolutions to the quantum measurement problem, most notably spontaneous collapse theories, as well as the many worlds interpretation of quantum mechanics in which every possible quantum outcome actually happens, but each takes place in its own quantum universe. It's not a particularly new idea, being introduced way back in Hugh Everett's doctoral dissertation in 1957, but it remains a leading, if controversial, contender for how quantum reality actually operates. In this third conversation with physicist and author Carlo Rovelli, we are going to continue our exploration of quantum mechanics and this mysterious transition from a haze of quantum possibilities to something like the definite world we each experience, because Rovelli himself has developed his own theory for how this may come about. All right, let's jump in. Carlo Rovelli is the director of the Quantum Gravity Group at the Center for Theoretical Physics at Aix-Marseille University in France. He is a co-founder of the Loop approach to quantum gravity and an author of several books popularizing science. Please welcome Carlo Rovelli. So, thanks so much for joining us. Really appreciate
Brian.
it.
It's a really pleasure and honor.
So I think you've heard, some of the discussions about quantum mechanics, the quantum measurement problem. Where do you come down? Is the quantum measurement problem something that's vital to understand in your view? Do you think you have a solution to it? Where do you come down on it?
I actually agree with much what I've heard from Elise and from Sean. I do think that it's a crucial, open problem, and that we should, or some of us should work on it. I think that we're still confused after a century, as you were saying, and that we do have some ideas of how to think about that. In the way you were talking with Sean, I think I agree. There are viable ideas. The question is which one is gonna be fruitful and useful and take us ahead in understanding the world. And there is a discussion going on which has evolved through the years and is still evolving. There are new ideas coming out. I am hopeful that at some point it will converge.
And so you heard that Sean is a great fan of the many worlds approach. Does that resonate with you, or do you look at that and you're like, much as he says, GRW isn't right, hidden variables is not right, do you look at many worlds and have a similar reaction, or is that something that you're in favor of as a viable approach?
I am exploring a different direction.
Which is a polite way of saying I don't like that, which is very nice.
Yeah, but it's important. I don't think the many worlds it's wrong. I think it's a possible way of looking at the world. I think there are other possible ways of looking at the world, and I think we should work through that.
Yeah.
Sean at the very beginning started by saying the first choice that we have is how to think about the wave function.
Yeah.
That's and one option is to say, okay, Schrödinger wave function of the quantum state, that's a real thing. Okay, so if I start...
And can I just jump in just so people have a visual image in mind? That was like that blue wave. I'm
That's
sure
a
you
blue
all know that we
wave waving
had
at.
that encapsulates, say, for a given electron, the various probabilities of, say, being at various locations. You call it probability wave or wave function. Go from there, yes.
That's right. So one possibility is to say this blue moving thing is the actual stuff of the universe. That's what's going on. There is an alternative, which I find it more appealing for a number of reasons, which is to take the opposite perspective. Namely, that's not the thing. Okay, the thing is a particle, the actual particle. And that thing there is just a way we have to compute where the particles are going to show up next. In classical mechanics, before quantum mechanics, there is a very similar thing. There's a very similar techniques of using a wave all over to compute where the particle is going to go next. It's called the Hamilton-Jacobi
theory.
And you have something, and in fact, the classical limit of the Schrödinger wave function is the Hamilton-Jacobi. So one possibility to sort of try to get an intuition about quantum mechanics is to think, well, that's just our calculations, our way of thinking what's going to happen next. And since, as you have been all emphasizing a lot, the first great discovery of quantum mechanics is that it's probabilistic. Even if you believe in underlying deterministic theory, you, like anybody else, you're not going to say whether the spin will go up and down, right? So it's intrinsically probabilistic as a limitation of what is going on.
Yeah.
Then it means that what we can do is a probability calculation. And that's wave thinks is a probability calculation. That's what Max Born clearly got the Nobel Prize for understanding that. But the probability calculation, of course, it jumps, right? If I don't know...
You're saying simply because you know more?
Yeah,
after,
I didn't know enough. I mean, I don't know what's the weather tomorrow. I have a probability that the weather comes out. It's one of them. And then my knowledge jumps.
When tomorrow happens.
Yes, when tomorrow happens. Or even, if I don't know who won a certain game, and just because it has already happened, and I don't know it, when I know it, my knowledge jumps.
But it's only your knowledge that jumps, right? There are other people who perhaps were at the game. They already have that knowledge. So you're describing a potential view of the world where different observers would be in very different levels of quantum.
Let me get there in two steps.
Yeah.
So let me backtrack one second.
Yeah.
Because there's one thing which is rarely said about quantum mechanics, which to me seems the core of the theory, which is granularity, discreteness, quantum, quanta.
Yeah.
In the discussion about the meaning of quantum mechanics, we tend to forget that, and I think this is wrong. Quantum mechanics came out as a description that things we thought were continuous are actually not continuous. Jumps are great. For instance, light gets to me as photons, individual photons. If
little bundles of light that are hitting you.
If I have a screen, lights get here. If I look sufficiently carefully, just one dot here, one dot here, one dot here, one dot here. Or, I don't know, atoms have discrete orbits, right? And the electron jumps from one to the other, and so on and so forth. There's all this discreteness at the basis of quantum mechanics. Which means that it tells to me that if you want to think about quantum mechanics, we don't have to add things, there is less. So the electron is here, the electron is there. This seems to me the indication. So now let me come to your question.
Yes.
One way you pose the question is, what is a measurement? Okay, and that's, I think, the right question. It's the right question. You asked to Elise, you asked to Sean. The way I think could be useful, think about quantum mechanics, which is called relational quantum mechanics, is to try to answer this question by saying everything is a measurement. Every time any two systems interact, they're measuring one another.
By definition, an interaction is a
interaction
measurement,
is a
regardless
measure.
of who's doing it, what doing it.
It's a measurement.
Yeah.
Yes.
Okay.
So the screen, the particle touch it, that's a measurement.
Yeah.
But also an atom here and the photon bounce it, that's a measurement.
Yeah.
Okay. And so the wave function is just telling us what is the way one system is going to affect another system. What's the probability distribution of the way it's going to affect it? Now this works at one condition, and that's a hard point, and that's, I think, what quantum mechanics is deeply telling us. The condition being that the actual result of the measurement, the act of interaction, doesn't display a property of, say, the particle, but displays a relative property of the particle with respect to the screen. That's contextuality. Now,
so just so I can understand, if I'm measuring like our spin-a-half particle that we had before,
and you see it up,
and I see it up, you're saying it's not that the particle is up.
That's right.
It's that I and the particle stand in a particular relationship.
That's right.
Which is what we would normally call the particle up, but it's not a property of it, it's a property of us both.
That's correct. That's correct. Which means that every time you say the particle is up, which is fine, what you really should say, the particle is up with respect to me. Exactly. Yeah. And if you do that, I believe things go in order. So the so-called paradoxes of quantum mechanics go in order. The cat, which interacts with the quantum stuff in the box, the Schrödinger cat, it's either alive or dead with respect to himself. And do you have a cat? Yeah. That's right. So with respect to the cat is just alive or dead because the quantum object did this or that. But with respect to me, who are outside the box and looking at that, careful, the cat is neither dead nor alive. Because with respect to me, neither of these two are realized. So whatever I see next, I shouldn't assume that with respect to me, one of the two happens.
And
this is the core of
just want to make sure, and
mechanics.
it's clear in your approach, obviously it must be, but that if two different observers are interacting with the same object, they'll never find any kind of contradiction. You know, if the spin up is not a property of the particle itself, you might wonder that, you know, person A stands in the spin up relationship, but person B might stand in the spin down relationship.
That's exactly what has been discussed. I mean, this idea of relational quantum mechanics came out in the 90s.
Yeah.
And it slowly grew, sort of number of people interested grew slowly. Now there is a lot of paper coming out. And for
you started it. This was initially your idea, is that correct?
That started off a paper of mine in the 90s.
Yeah.
But then was developed, but first by philosophers, a number of, including important philosophers. Bas van Fraassen, for instance, wrote a paper on it, and others. Now is getting more in the foundation of physics attention. And the first part of the discussion was always, does this create contradiction?
Yeah.
There was a lot of debate, consider this case, this case, this case. It doesn't. That's the point. There is a coherence in quantum mechanics itself, so it doesn't create contradiction. So the idea here is that instead of adding many worlds, or adding hidden variables, or adding a GWR
collapse,
extra collapse, another take away. The properties of any object are always relative to something else, and objects have properties only when they interact.
Now, in some sense, is there a many worlds-like quality to this description?
There is a many worlds. It's not so different from many worlds,
right.
in a sense.
Because if the particle isn't spin up on its own and it's a relationship, then the other possibilities, in some sense, are still there.
Still there, yes. In fact, it's still there. The idea that properties are relational, it's sort of all over physics. If you think the great step in going into Newtonian physics in the Renaissance with Galileo, Kepler, and so on, was to answer this question: what is the velocity of an object? Right? Is this moving? No, it's not. Okay.
With respect to us.
With respect to us. But it's moving with respect to the sun. Okay. So the velocity of an object is not a property of the object. It's a property of the object and something else.
Sure.
It's a relational property. And in a sense, the relational interpretation of quantum mechanics is making this very general. Not just velocity, but all the properties of an object have to be thought relationally with respect to something else.
Now, when you say all, presumably not really all, like the mass of a particle presumably is not in that category.
Contingent.
Contingent properties.
The one that change,
That
the
can
one
change,
that is
yeah.
phase-space.
And so in this approach, how does this illuminate, say, entanglement? You know, so I mean, I asked an unfair question saying, you know, you got these two distant particles, you measure one, you find it up, the other one is down. I said, how does that happen? And of course, we don't really have a story to tell that's really convincing in the usual approach. Do you have a story to tell in this relational approach that sheds more light on it?
Yes, it is a story which is doesn't take away the strangeness of the phenomenon. The phenomenon is strange and remains strange. It's also a story that shifted it into the strangeness of quantum mechanics itself. The story is the following. If you imagine that you measure something here and you measure something there, you're cheating. Because who is seeing here and there at the same time? Nobody. To compare that they've seen the same thing, you have to wait until they communicate to one another. And once they communicate to one another, say the information is sent, then you can compare so now let's see what is the world with respect to the final observer that gets the information.
Yeah.
There's no non-locality anymore because all the information is so.
But when I unravel that story, wouldn't I still need to explain why there's this correlation that whenever this one's up, that one's down. Whenever this one's down, that one's up, which would be surprising if they're both just 50-50 up and down and not somehow talking to each other.
Because you are...
Oh, you're again saying I'm assigning the property to the particles still.
Exactly.
Yes. Okay.
Exactly. So the idea here is that think that the mistake is always to assign absolute properties to particle instead of relative to something else.
And so, are you able to push this approach to say relativistic quantum mechanics? I mean, is this something?
Yeah. It's sort of. In fact, it's. I got to there in a long way through quantum gravity because that's my job.
Sure.
to try to write a quantum theory of gravity, even if I think the problem of quantum mechanics is separate by the problem of quantum gravity. And nevertheless, and I very much agree with Sean in that, I think that once we understand better quantum mechanics, this should help us to understand better quantum gravity. And I do agree with Sean a lot that there is something deep to understand about the quantum structure of space-time by somehow a clear idea about quantum mechanics. And let me step back a moment. I started by saying granularity, discreteness. See, quantum mechanics has a constant, h bar.
Yes.
Okay? Unless we understand that constant, we don't understand quantum mechanics. So any interpretation of quantum mechanics should tell me what this constant is, h bar, right? It's a number, 6.31, whatever.
I like the number 1 in the correct units, but yes, you can
one
use
in the
that
correct
too.
unit.
Yes.
It's like the speed of light,
Yes.
right? But the speed of light, we know it is. It's the fastest thing at which I can go in some proper sense. And that number, it's just the size of the granularity.
Yes.
It tells us how big are the quanta. Okay, that's why it's the core story of quantum mechanics. Now, when you apply quantum mechanics to gravitational field, to gravity, as you were saying with Sean before, gravity is different in the sense that it's actually space-time itself that moves. So, like the light. If you look into small, it's photons. Space-time, if you look into small, should be quanta of space. And that h bar should say how big are this quanta of space, together with Newton constant and so on. And one gets to the Planck scale, and that's the core result of loop quantum gravity, the quantum theory of gravity on which I'm working. It's a tentative theory. We don't know if it's right yet. So the structure of space-time is all this quanta this granular. So space is this grain of space, which are quanta of space, like photons, but they don't live in space. They make up space themselves, and the way they're connected to one another, it's one in relation to another one. And if we think about how we think about space, the space-time region has a boundary, and we describe how it affects the rest. And in quantum mechanics, we take systems and we describe how the system affects another system. And the two things should go together, I believe. And so this relational way of thinking should help us in that direction.
You know, we only have a few minutes left, but I can't help but following that line of discussion a little bit further, because I think as many in our audience know, you know, I work on an approach to quantum gravity string theory.
Of course, you were one of the main contributors.
Well, among many, many others. But, you know, what we have found, and again, as Sean was using it, is the royal we, many in the field have found that there's now evidence that the fabric of space-time in a string theoretic approach is stitched together by the threads of quantum entanglement, because calculations have been done where, I mean, in our visuals that we showed, spin up and spin down, we're connected by this sort of invisible line of quantum entanglement. There can be regions of space that are connected by lines of entanglement, and we mathematically can cut those lines of quantum entanglement, and the space falls apart into little tiny pieces and then disintegrates completely once the entanglement is fully dissolved. So from our perspective, that's given a lot of insight. I mean, it resonates with what you're saying, but a very concrete means by which entanglement would be the very ingredient that holds space-time together.
Yeah.
Are you finding like I mean, obviously a different language, but are you finding a similar way of thinking about space-time and loop quantum gravity?
Yeah. You know that, we've been working very different in opposite directions of quantum gravity, but that aspect of string theory, I found it very much interesting and intriguing, and it does resonate with something very similar that happened in loop quantum gravity, including in the mathematics. So the structure of spin networks is a structure of entanglement between little Hilbert spaces here and there. And I do believe that we have not really clarified yet. We don't have a clarity about that. But there is something convincing in the idea that the notion of contiguity, who is attached to whom, and the sort of entanglement, they're related.
Yeah.
Because, you see, the core of modern physics after Maxwell in the last century is locality. So what is locality? Locality is the idea that interactions are local. So you don't interact with something far away. You in some sense, dynamically interact with something nearby. But you can turn this around. What does it mean to be nearby? It means you can interact with it directly, okay? And if you interact with it, you get entangled. That's exactly what the core of somehow the relation interpretation is. As soon as you interact, you're entangled from the perspective of something.
Right.
So between entanglement, interaction, because of locality, and space-time contiguity, there should be a common thing. And I think that's the beautiful, slow understanding and unraveling of quantum gravity which is happening nowadays.
So let me end on a question that I asked in one way or another to both Elise and Sean, which is, we've been at this for a long time. We have yet to fully unravel it all, but we're making progress. But what do we lack to get to some final, complete understanding of quantum mechanics, and hopefully then be able to apply it to issues like the quantum nature of space-time? Is it experiment? Is it better mathematics? Do we need to use AI systems, or do we not have the brain power? What do you think it is?
I think just time, namely working on it. let me challenge one thing you said. At some point you described the advancement of physics, of course you were oversimplifying, you know, by sort of, we had a clear metaphysics, everything was clear until...
In the old days.
In the old days,
Yeah.
and then quantum mechanics, experiment come out, and then
Yeah.
you're in the dark. Of course, that's not true, right? I mean, when Maxwell wrote his equation, everyone was confused what this is about, including Maxwell himself.
And they were very messy equations in the early days.
It was a very messy equation, it was incomprehensible, and he thought that there was really matter pushing and pulling and rotating them. It took Einstein to understand that that's really not the case. And so on. I mean, there was confusion all over.
Right.
So being in a state of confusion is not really a characteristic of our time. And when Copernicus, I'm even going even before, did the so-called Copernican revolution, it's not everybody jumped up and said, oh yeah, right, we're moving and we have a new world picture and that's our world picture. It took a century to go to Kepler and Galileo, convincing everybody that actually makes sense we're moving. And everybody was horrendously confusing exactly because of what we were saying before. We're not moving, how come we're moving? So you have to completely rethink what moving means. Okay, and then of course comes Newton and everything. And so on. So I think that takes time. Between Copernicus and Newton finally clarifying, it's a century and a half.
Yeah.
Quantum mechanics is only a century. We are. What does it take? It takes, I believe, people thinking about that, writing paper, debating, getting angry to one another. No, you're wrong. No, you're wrong. That's fine. That's how science works. Developing theories. And then slowly, at some point, I believe some perspective will become more fruitful and will come to agree on a view. I think that my grandchildren, I don't have children. I mean, I think that in two or three generations, if we don't kill one another with the atomic bombs, which is if we survive, people will say, well, of course the Schrödinger cat is like, it's obvious, isn't it? Like we say, of course in Sydney people are upside down, right? It's obvious.
Yeah, no, and it's an amazing thing, even with quantum mechanics today, graduate students speak in terms that are so intuitive.
That you and I are...
Yeah, but like a little bit, you know, and go a generation before, and it would have been even more difficult to acclimate to this new way of thinking about things, which becomes fluid later on. So in short, it's like 3 cheers for confusion, because that's the natural place for us to be.
And let's not forget that quantum mechanics is 100 years old, but quantum mechanics has unbelievable predictions that nobody believed, like entanglement at large distances, where many people were thinking, oh yeah, but that cannot be true.
Yeah.
And the solid, convincing experimental support that quantum mechanics is actually right is not so old after all. I mean, the last Nobel Prize with Zeilinger and company, basically it's a Nobel Prize for people who are saying, look, quantum mechanics is right.
Yeah. And so if I place your prediction in more personal terms, when my grandkids are adults, perhaps we'll have this solution in hand, which would be certainly a wonderful outcome if
I
we
hope
can get
so.
there.
We probably won't be there, but...
Probably not. Join me in thanking Carlo Rovelli.
Thank you very much.
Wonderful.
Pleasure.
So perhaps, as Carlo Rovelli suggests, quantum weirdness is bound up in our mistaking relative qualities of objects or particles, qualities that are in relation to another object or particle or observer, mistaking those qualities for intrinsic qualities like mass and charge. It is a promising approach that no doubt will continue to be developed. All right, that is the third in our series of conversations on quantum reality. If you've not seen part 1 with Elise Kroll or part 2 with Sean Carroll, I encourage you to do so, as those conversations covered a lot of ground on the basics of quantum theory, the quantum measurement problem, and the many worlds interpretation of quantum mechanics. Let me leave you with one final thought. In these conversations, we have focused on the frontier of quantum mechanics, the aspects of the theory that we are still struggling to fully understand. But bear in mind that for all the things we've yet to fully sort out, we can use quantum mechanics to make the most precise and accurate predictions in the history of human thought and exploration, while also being able to leverage those insights into building the most sophisticated technology that our species has ever achieved. So while there are deep questions that remain, we should be rightly proud of all that we have achieved. All right, thanks for joining us. And until next time, from the World Science Festival, I am Brian Greene.